Assalamualaikum and a very good day to everyone. Respected to Sir Amirul Mukminin bin Muhammad Razi, our soil mechanics lecturer and fellow classmates. We, from Group 2 of Semester 5, Session 5 Act 3, would like to begin by expressing our heartfelt thanks to Sir for his guidance and support throughout the completion of this assignment. Today, we will be presenting our topic entitled Types of Soil. This presentation will cover the different categories of soil, their characteristics, and their importance in the field of civil engineering, particularly in relation to soil behavior and foundation work. We have done our best to prepare and present the information clearly and concisely, and we hope it will be both informative and engaging for everyone. Without further delay, let us begin our presentation. First thing first, I would like to introduce my group member. My name is Eva Fauzana binti Abdullah and my ID number is KNN233610437. And second is Muhammad Fatul Aiman bin Abdul Rahman. His ID number is KNN233610467. And thirdly is Adam Lubais bin Saiful Azri. His ID number is KNN233610394. And lastly is Muhammad Shahir bin Nurmizan. His ID number is KNN233610343. So, I would like to start with introduction of soil. The top layer of the earth crust is a dynamic and vital natural resource that supports life and construction activities. Its properties vary based on climates, parent material, and biological activity, making soil investigation essential in engineering. Each soil type such as laterite, loam, and clay, it has distinct characteristics that affect its suitability for foundation and structural use. This report explores the origin, physical traits, and construction relevance of these three soils, emphasizing the importance of proper site investigation through field tests, lab analysis, and profiling to ensure safe, efficient, and sustainable engineering outcomes. Next is objective. The main objective of this report is to study and compare the properties of three common soil types such as clay, loam, and laterite to evaluate their suitability for construction. This includes identifying their physical characteristic, origin, drainage performance, moisture behavior, and load-bearing capacity. The report also aims to highlight the importance of soil investigation through field work and laboratory testing, and to interpret key geotechnical data such as groundwater levels and soil stratification. Ultimately, it promotes awareness of soil behavior and the need for appropriate treatment or stabilization techniques to ensure safe and effective engineering solution.
Hi, I'm Adam. I'm going to explain about the three chosen soil of our case study. In civil engineering, soil is a crucial natural material and is important in designing and building structure in immense all construction endorsed because whether they involve a building, road, bridge or dam depends on soil, either as a foundation material or as a part of the construction itself. Therefore, it is essential for engineers and construction professionals to comprehend the characteristic and behavior of various soil types under different environmental conditions and loads. This report focuses on these three specific soil types due to their prevalence in actual construction sites and their unique engineering behaviors. Every one of the soil possesses distinct challenge and opportunities, and comprehending this can result in to improve design solution and safer structure. As an example, certain soil may need to be compact or stabilized prior to use, while others may necessitate full replacement if they are determined to be weak or too expensive. Alright, so the chosen soil for this case study each provide a distinct profile. For instance, laterite soil, which is prevalent in tropical environment and significantly affected by strong chemical weathering. Due to its mineral composition and hardness after drying, it is commonly used for roads and structure fill. So the second soil is loam soil, a well-balanced blend of particles which is often regarded as optimal for farming and lightweight civil engineering projects. It is very versatile because it can keep water and nutrients while still enabling adequate drainage. And the third soil is clay soil, which is we often hear Clay soil often troublesome because of its high plasticity and sensitivity to moisture. It is also very common, while it must be handled with care in construction project. It serves valuable purpose in impermeable barriers and manufacture items such as bricks. Right, so understanding the texture or color of these soils is only part of the analysis. This entails a true investigation of physical traits like grain size, structure, and consistency, chemical properties such as mineral composition and reactivity, and engineering characteristics such as bearing capacity, permeability, and cohesion. It is essential for engineers to assess if the soil can be safely bear a structure, if it will experience settlement or movement over time, and if stabilization or replacement is necessary in every project. Okay, so that's all from me.
Assalamualaikum and hi everyone. In this section, I'll be talking about the construction stability of the three selected soil types, which is laterite, loam, and clay. Each of the soil respond differently to structural loads, water condition, and environmental exposure. So understanding the behavior is essential for choosing the right material in construction. So let's start with laterite soil. Laterite is quite unique because it hardens immediately when it's exposed to air. When it's moist, it's easy to dig and shape, but as it dries, it becomes almost rock-like. This makes it especially useful in low-cost rural infrastructure, such as village roads, small buildings, drainage systems, and pavement subgrades. When compacted well, laterite offer a moderate to good bearing capacity, making it suitable for light to medium structures. However, a major drawback is that its strength is highly affected by moisture. Without proper treatment, water infiltration can weaken it over time. One big advantage of laterite is its high porosity and permeability, which means water drains quickly. This makes it a great choice in rain-prone areas where drainage is key to preventing foundation problem. Next, we have loam soil. Loam is often seen as the ideal soil in both agriculture and construction because it strikes a good balance, about 40% sand, 40% silt, and 20% clay. This gives it a perfect blend of drainage cohesion and compaction properties. In construction, loam is well suited to from small to medium structures like single-story homes, sidewalks, and light pavement. It offers a moderate bearing capacity, and because of its structure, it's easy to work with on-site, saving time and also resources. However, loam is best for low-load application. It's reliable when properly compacted and maintained at the right moisture level, but it may not be ideal for heavy construction without additional supports. Finally, let's talk about clay soil, perhaps the most challenging of the three. Clay contains very fine particles which make it sticky and plastic when wet, but hard and cracked when dry. What makes clay tricky is its high shrink wear potential. It expands significantly when wet and shrinks when it dries. This causes heavy or settling, which can damage foundation walls and pavement. Because of this, clay is often considered unsuitable for shallow foundations unless the structure is very light or the soil has been properly treated. Despite its issue, clay can still be useful in construction when handled correctly, but it requires careful planning, moisture controls, and sometimes soil stabilization techniques to ensure structural safety. Finally, to summarize all, laterite is best for light to medium structures, especially when in wet climates. Just make sure it's protected from water infiltration. Loam is flexible and easy to work with, ideal for residential and light infrastructure. Clay, while common, demands extra care due to its tendency to expand and contract with moisture. So choosing the right soil isn't just about what's available, it's about understanding how that soil will behave over time under environmental and structural pressure. And that's all for me. Thank you.
Okay, Assalamualaikum everyone. I want to talk about the 6.2 objective. The first one, in order to ascertain the engineering and physical properties of the soil layers at the construction site. And the second, to determine the soil profile and stratification below the surface. The third one, in order to evaluate the settlement characteristic and bearing capacity of the soil. And the fourth, to assess the groundwater condition, comprising the depth of the water table and seasonal fluctuation. And the last point is to identify the presence of any problematic soils or geotechnical hazard. Okay, for the 6.3, we have three other information. For the soil, we have the three information. The first one is soil stratigraphy. This involves identifying how different soil layers are arranged beneath the surface. Each layer has unique properties, and understanding them help determine the right foundation depth, locate weak zone, and predict soil performance under load. The second other information is groundwater condition. Groundwater fills the space in soil and rock underground. Knowing the water table depth is important, as high ground underwater can weaken soil strength and increase the risk of instability, rooting, or foundation problem. The third one, problematic soils and geotechnical hazard. Some soils like clay, peat, or loose sand can behave unpredictably with moisture or load change. Detecting them early help avoid structural issues, costly delays, or failure during and after construction. Okay, for the 6.4, we have the sample. For the depth 0.0 to 0.5 meter, the soil description is topsoil, dark brown, soft with organic matter. The soil classification is OL, organic loam. The moisture content is 38%, SPTN value is 4, and the remark, high organic content, unsuitable for foundation. For the depth 0.5 to 1.5 meter, the soil description is silly clay, reddish brown, soft plastic. Okay, for the soil classification is CL, low plasticity clay. The moisture content is 30%, the SPTN value is 8%, and the remark, slight plasticity, low bearing capacity. Okay, for the depth 1.5 to 3.0, the soil description, sandy silt, light grey, medium dense. For the soil classification, ML, low plasticity silt. For the moisture content is 22%, the SPTN value is 15, and the remark, good drainage, moderate bearing layer. The depth and the next, the depth is 3.0 to 4.5. The soil description is well graded sand with fine gravel, dense. For the soil classification, it is SW, well graded sand. For the moisture content is 12%. The SPTN value is 28. Remarks, suitable for shallow foundation. And for the depth 4.5 to 6.0, the soil description is clay sand, dark brown, stiff, moist. And the soil classification is SC, clayey sand. For the moisture content is 18%. SPTN value is 20. The remarks, acceptable strength for foundation use. And for the last is 7.0, conclusion. This report has provided an in-depth evaluation of 3 significant soil types, such as laterite, loam, and clay, by examining their formation, physical properties, and engineering suitability. Each soil behaves differently under load and environmental conditions, making soil identification and investigation critical in construction. Laterite soil, common in tropical climates, offer good drainage and become strong when dry, making it useful for roadworks and rural structures, but it can weaken when wet, requiring stabilization for structural use. Loam, with its balanced composition of sand, silt, and clay, it is easy to compact and supports vegetation well, making it ideal for residential buildings and landscaping. Though careful moisture control is needed to avoid long-term settlement. Clay, while cohesive and moldable, is the most problematic due to its tendency to expand when wet and shrink when dry, which can cause foundation damage if not treated or reinforced. Proper soil investigation, for including borehole drilling, lab tests, and groundwater observation to help engineers to determine safe foundation depth, anticipate soil behavior, and avoid failures. Ultimately, understanding the soils allows for safer, more durable, and cost-efficient construction, supporting sustainable engineering practice and ensuring the long-term success of infrastructure projects. That's all from me. Thank you.